Hello everyone! I had lots of fun solving the two problems in today's video, so I hope you enjoy the video as well. We'll be going over two problems from the recent Putnam 2022. The first being B3, which involves the coloring of the positive real numbers, and I classify it as a combinatorics problem, but you can let me know at the end of the video whether you agree with this classification. The other question we'll be covering is A5, which is a game between Alice and Bob, and this is another fun combinatorics problem. So without further ado, let us take a look at the problems. For B3, we have a slightly long problem statement, and it's easier to understand it through a diagram. So let me take you through the diagram instead. So what we have here is a positive real line, and we are supposed to assign to each positive real number a color, either red or blue. So from this coloring of the positive real line, we are supposed to produce a next coloring. And to produce this new coloring, this is the rule that we will be following. So for a given real number R, what color does it get? Well, if there exists 2 points in the previous coloring, they are of distance R apart and they are of the same color, then the real number R will now be color red. It doesn't matter if the same color is both red or both blue. Now, on the other hand, if a real number S is such that no 2 points of distance S apart is of the same color, then the real number S is now colored blue. So following this rule, we can now have a new coloring of the positive real line, and now this coloring becomes the old coloring from which we produced a next coloring, and so on. If we iterate this recoloring process, the question is, will we always end up with all the numbers red after a finite number of steps? So this sounds like a crazy problem because firstly, the real numbers are so rich and it's hard to imagine a coloring, any coloring from at the start, and then to translate that into a new coloring and so on, other than the very abstract rule that I just described. So let us first try and understand this coloring rule better. Okay, what we'll do is we'll call C0 the initial coloring, which can be anything. And then from that, we get C1, C2, C3, and so on. So we want to understand what happens if we have a blue point at X at some time CT, right? And of course, because C0 is a coloring that you can choose arbitrarily, there's no rules for C0, right? So it's only meaningful to think what happens if there's a blue point for some t greater than or equal to 1. So let's take a look at this scenario and find out what are the implications. So, but based on the coloring rules, we know that in the previous time, any 2 points of distance x apart will definitely be of opposite colors. For ease of notation, I'm going to use x and 2x. And we know that they are of opposite colors, let's say 1 and 2. It doesn't matter red, blue, or blue, red. Okay, similarly, 2x and 3x are of opposite colors, 3x and 4x are of opposite colors. So we have this situation here. Now, this is the key observation that will bring us far. Let us take a look at the midpoint of 2 points of opposite colors. So in this case, let's take a look at 3x over 2, which is the midpoint of x and 2x. This means that no matter what color you choose, it will either have the same color as x or the same color as 2x. Which means that there will definitely be a pair of distance x over 2 that are of the same color, either the left pair or the right pair. This tells us that at time t, the point x over 2 is definitely red. So we use this midpoint trick again, this time with the pair with the points x and 4x. So the midpoint is 5x over 2. And again, because x and 4x are of opposite colors, no matter how you color 5x over 2, you will either have a left pair or the right pair being of equal color, which means that there's a pair of points of distance 3x over 2 apart that are of the same color. So we know that 3x over 2 in time t is definitely red as well. And this actually gives us already our first key implication, which is that in the next time period, because x over 2 and 3x over 2 are of the same color and distance x apart, by definition, the point x must be red. And we can apply the midpoint trick again at time t. This midpoint is sandwiched between 2 opposite colors. No matter what color this is, it means that there is some pair of distance x over 4 that is of the same color. So at the next time step, x over 4 is of color red. So what is the implication we have? If x is blue at some t that is greater than or equal to 1, then at the next time period, x and x over 4 are definitely red. So this is a very important implication. It gives us some rules that we know relating one time period to the next time period that is quite easy to understand. Now from this, we can actually already conclude the problem. This is a very powerful observation. I claim that all numbers will be red by the time t equals 2. And this looks completely surprising because it's mind-blowing. Like, no matter how you color t equals 0, by t equals 2, everything will be red. And the argument is actually not complicated. Suppose, on the contrary, that some point x is blue at time t equals 2. Let's take a look at time t equals 1. Again, we know that x2, x3, x4, are in alternating colors. So I call them 1, 2, 1, 2. The question is, firstly, can it be blue, red, blue, red? No, because if it's blue, red, blue, red, x is blue here, and then we get x is blue again in the next time period, which is a contradiction. Can it be red, blue, red, blue? Again, no, because if it is blue here, 4x is blue, but x is blue again. Remember, when you divide by 4 in the next time period, we will now move from blue to red. So again, this is not possible. So this leads to a contradiction. And yeah, that is all from problem V3. It like the bliss comes like very suddenly, right? And yeah, this is quite surprising, but making the observation in the green box is really the key step. So right now we are going to look at A5, but before doing that, if you have been enjoying the video so far, make sure you subscribe, like, comment, and share with your family and friends. It will really help me out for this video. So without further ado, let us now take a look at A5, which is a game between Alice and Bob. Okay, so for this problem, we have Alice and Bob playing on the board consisting of 2022 consecutive squares, and they take turn placing tiles of length 2 on this board. So Alice goes first. Let's say Alice puts here. Now the key rule is that a tile must not cover a square that is already covered by another tile. So for example, Bob cannot put his tile here because it overlaps with another tile that has already been placed. So maybe let's say Bob puts here. Alice can still put here because it doesn't overlap with another tile, and so on. And the game only ends when no tile can be further placed according to this rule. Now, Alice will try and maximize the number of uncovered squares at the end of the game, whereas Bob will try and minimize it. The question is, what is the greatest number of uncovered squares that Alice can ensure at the end of the game, no matter how Bob plays? So this looks like an interesting problem. Let's do a quick brainstorm on how might the game evolve if Alice and Bob tries and play cleverly. Of course, this does not constitute a proof. We're just brainstorming for now. If Alice wants to guarantee a lot of uncovered square, it might seem smart to put the first tile here because it forces this square to be uncovered even at the end of the game. And then what might Bob do? You might think, yeah, maybe Bob wants to put here so that, you know, it prevents any gaps and any uncovered square from happening between A and B. But actually, the more clever thing to do is to put here, because now it will force someone eventually to put a tile here, and there is no uncovered square all the way to the 7th square. So this might be something that Bob might want to do, and then of course Alice want to create a uncovered square and put here and so on. So it sounds like if both players play optimally, you will end up with blocks of 7, and then basically the last block of 6, right? Alice will create a uncovered square, and Bob, has no choice but to create an uncovered square. And it sounds like the answer should be 290. So this is, of course, a very hand-wavy description. It does not constitute a proof. And the difficulty is that actually it's very hard to come up with a rigorous proof. It's as rare as a shining celebi. And a lot of proofs say like, oh, it's optimal for Bob to put here next and then Alice to put here next. But it doesn't consider the scenarios where Bob might put like some random far away like square, in the hope that global in the long run is actually a more optimal solution. So I'm going to present a proof that is given by this user on AOPS forum, and it's a really elegant proof that is watertight. Okay, so this proof consists of two parts. The first part will show that Alice can guarantee at least 290 uncovered squares. So to do this, I'm going to specify a strategy of Alice. So on her turn, she always places a tile such that it creates a one gap to its left. So for example, on the first turn, she is forced to put here because then that's the only way she can create a one gap to its left. Let's say Bob places anywhere, it doesn't matter. Then Alice can maybe put here because it creates a one gap, or she could put here because it creates a one gap. So basically, this is the rule that I impose on Alice that she'll follow. And let's continue this until the point where it's Alice's turn and she cannot put a tile down while keeping to this rule. Or it could also be the case that the game has already ended. And let us analyze the situation when this point is reached. First observation is that all gaps must be of length at most 2. Why is that so? If there's a gap of length greater than or equal to 3, let's say here, then Alice is still, firstly, the game hasn't ended because you can still put a tile down. And secondly, and Alice can still put a tile down while keeping to the rule. Specifically, she can put down a tile while creating a one gap. So all gaps must be of length at most 2 at this point of the game. I'm going to define a few variables now to analyze at this current point of the game. So at this point, let A be the number of tiles Alice plays, B be the number of tiles Bob plays, U be the number of 1 gaps, and V be the number of 2 gaps. As mentioned, there's no gaps bigger than of length greater than or equal to 3. So first observation is that all the 2022 squares either is covered by Alice's tile, Bob's tile is a part of a 1 gap or is part of a 2 gap. So we have this equality here. And the second observation is the rest of the game will basically proceed by filling up the 2 gaps, and the 1 gap will be left over as uncovered squares. So essentially, we want to show that U is more than or equal to 290. That will prove the first claim. To do this, we will look at a few inequalities. The first one is quite easy, B less than or equal to A. And this is true because basically Bob only places a tile after Alice places a tile. So Bob cannot have possibly placed more tile than Alice. Okay, the second inequality we'll show is A less than or equal to U. And this is a very important one to follow because this line of logic will be used over and over again for the rest of the proof. So why is A, the number of tiles Alice plays, less than or equal to U, the number of 1 gaps? Essentially, each tile that is placed by Alice can be mapped to the one gap that it created. So this is actually an injective map from Alice's tiles into the 1 gaps. There could be more 1 gaps because maybe Bob placed a tile down and created 1 gaps, right? But Bob places a tile down and created a 1 gap, but we don't care about this. We only know that whenever Alice puts a tile down, it creates a 1 gap, and this 1 gap stays all the way to this current state of the game. So there's an injective map from Alice tiles to 1 gap. So this inequality holds. Now on the flip side, we are going to show V minus 1 is less than or equal to B. V refers to the 2 gaps, right? And this time we are going to reason in the opposite way. Each 2 gap that is created is definitely due to Bob placing a tile to its right, except possibly the rightmost 2 gap. What does this mean? If we look at each 2 gap and we look at the tile to its right, it is definitely a Bob tile. So we can create a mapping from 2 gaps to Bob tiles. Why is this so? Well, it cannot be an Alice tile because Alice wouldn't have placed a tile down that leads to a 2 gap. She only places a tile down that gives a 1 gap. So each 2 gap can be mapped to the tile to its right, which is a Bob tile. And of course, the rightmost 2 gap maybe has no tile to its right. So V minus 1 is less than or equal to B. So if you put all these inequalities together, basically we have this string of inequalities which we can substitute in to the equation here to express in terms of u. So we have 2022 less than or equal to 7u plus 2. This gives u is at least 288.5 something, which means u is at least 289. But if you look at this equation again, u is clearly an even number. So we actually have u is at least 290. So that proves the first part of the solution. And the second claim is actually quite similar, but there's one catch that I would like to point out. So stay with this proof. There's a very subtle and sneaky gap, which the original poster actually missed, and some other comment in the AOPS forum fix it for him. Okay, so for this claim 2, we are going to show that Bob can guarantee at most 290 uncovered squares. This time, I'll specify a strategy for Bob that it is able to force down this number of uncovered squares. On Bob's turn, he always places a tile such that it creates a 2 gap to its left. So don't care how Alice plays, Bob could, for example, instead he could either place here because it creates a 2 gap, or he could place here because it creates a 2 gap. So same thing, I'm going to continue until the point where it's Bob's turn and he cannot put a tile down while keeping to this rule, or possibly maybe the game has ended already. At this point, all gaps are of length at most 3. Why? Because if there's at least a gap of at least length 4, Bob will definitely be able to put a tile down while keeping to the rule. So I'm again going to define a few variables. We have A, number of tiles at this place, B, number of tiles Bob plays, U, V, W being the number of 1 gaps, 2 gaps, and 3 gaps respectively. And we again have this similar equation. And this time, as the game continues past this stage, 2 gaps will be filled, while the 1 gap and 3 gaps will each contribute to an uncovered square. So the end of game will have U plus W uncovered squares, and we want to give an upper bound of U plus W being at most 290. So again, we will look at a series of inequalities. B is greater than or equal to A minus 1. Again, because Bob places a tile after Alice places a tile, so Bob will have at least 1 short of Alice's number of tiles. Okay, next, V is greater than or equal to B minus X. What is this X? Well, let us first consider what happens if we try and prove V is greater than or equal to B. So we want to use our line of logic that we have been using all along, which is saying that each tile placed by Bob can be associated to the 2 gap that it created to its left. There's a flaw in this reasoning because when Bob places a tile down, maybe it created a 2 gap. But Alice could have foolishly, after that, played a move that fills up the 2 gap. And this means that actually there could be fewer 2 gaps than the Bob tiles, right? So to rectify this, we are going to let X be the number of tiles that Alice plays that actually fills 2 gaps. So any remaining, so the right statement could now be said that any tile that is placed by Bob and not subsequently left filled by Alice can be associated to the 2 gap that it created and the 2 gap that survived. So B minus X here is the first part of the statement. It can be injectively mapped into any 2 gaps that remains on the board at this stage. Okay, and lastly, we have this inequality where we basically use a similar line of logic as the claim 1. Each 1 gap and 3 gap is definitely due to Alice placing a non-X tile to its right. So again, look at each 1 gap and 3 gap. What is the tile to its right? It cannot be Bob's tile. It must be an Alice tile. And even better, it will not be an Alice tile that Alice placed to fill a 2 gap. So that's why we can injectively map 1 gap and 3 gap, except the rightmost one, possibly, into non-X's type of Alice tile. So we have this inequality here. So again, putting all these inequalities together, we can actually reach this 2022 greater than or equal to 7u plus w minus 10. So this gives u plus w at most 290.2 and u plus w at most 290. So that's all to the proof. It's a bit long. It sounds a bit complicated because it's an A5 problem, but this is really the most elegant proof I could find that is completely rigorous in terms of proving the answer. So hope you enjoy the problems that I covered so far. comment in the comment section below whether you enjoyed B3 and A5. So stay tuned to the channel for more math videos and see you soon.